Okay, hello, welcome back. So we have covered almost everything in configuration space. The only thing that remains is to find formulation to be able to write momentum of the system along these different um, configuration axes, or so the momenta that are associated with the generalized coordinates. Before we do that, let me remind you of some small detail. So recall that. So when we have a particle, we know the kinetic energy is 1/2 m x dot squared plus y dot squared plus z dot squared. So in Cartesian coordinates. We also knew that the momentum about x was m x dot. Comparing these, we can see that momentum is actually partial derivative of kinetic energy with respect to velocity along that direction. So we're going to use this notion to write the momenta about or in the direction of our generalized coordinates on Q's. So again, the setup is similar as before. Now consider a system. Why is this so close? A system of n particles and generalized coordinates qi. If you remember from previous video, if we have such a system, we can write the kinetic energy as a relatively big term. I equals 1 to n, j equals 1 to n, mij, q dot I, q dot j, plus summation I equals 1 to n, some big thing that let's call it ai of q and t times q dot I, plus another term, let's call it t naught of q and t. And going back to previous video, we remember ai of q and t was k equals 1 to 3n, mk partial xk partial qi partial xk partial t, and the t naught of this q and t is 1/2 summation k equals 1 to 3n, mk partial xk partial t squared. So these are the two terms that show up because we have this time dependence in our transformation equations. So remember, we had this, and from this kind of definition, where is it? Where was it? This. From this kind of definition, we can write my q, my momentum in the direction I, or the momentum that is associated with the generalized coordinate I, is this partial t partial q dot I. And if we do that, it's going to be summation j equals 1 to n of mij q dot j. Let me write it as mij of q and t to be more complete, plus ai of q and t. So that is the momentum associated with the direction qi, or with the generalized coordinate qi. So that's it. Maybe we can look at one example. Just to make sure the concepts sink in. Again, we have that particle moving in a 2D space. So it has two coordinates, x and y. And let's also have another set of generalized coordinates, r and theta. These are the polar coordinates. So my q1 is theta, my q2 is r. I have two generalized coordinates to describe the system. And my original coordinates x1, which is x, is q2 cosine of q1. And my second coordinate x2, which is my y, is q2 sine of q1. So I want to write the generalized momenta in these along q1 and q2. So to do that, what is the best approach? I'm going to need my partial derivatives. Do I need that? Well, not yet. So I'm going to need these masses M11, which, if you remember, is the summation of k equals 1. In this case, I only have one particle, so 3 times 1 is 3. Mk partial xk partial q. Let me write this in general form. Mij qi partial xk partial qj. So from here, M11 is going to be M partial x1 partial q1 partial x, well, this one is squared, plus M partial x2 partial q1 squared, which is M times partial x1 partial q1, that is q2 minus q2 sine of q1 squared, plus this one is going to q2 cosine of q1 squared. So I'll have sine squared plus cosine squared, which is 1. So I'll end up with is m q2 squared, which, notice, it is the moment of inertia of the particle about the center point O. So M21, do I need more space? Probably I need a little more space. M21 equals M12, which is M times partial x1 partial q1 times partial x1 partial q2 plus partial x2 partial q1 times partial x2 partial q2, which, if you write it, is going to be m times minus q2 cosine of q1 times sine of q1 plus another q2 cosine of q1 sine of q1, and they actually cancel out. So the off diagonals M12 and 21 are 0, meaning that there is no kind of coupling between these two degrees of freedom, or between the coordinates angle and theta. But this is not always the case. So if there are some couplings, you will end up with non-zero masses in what we call off diagonal, because you can think of it as a elements on a matrix. And the last one, M22, is M times Q partial x1 partial Q2 squared plus partial x2 partial Q2 squared, which is going to be M times cosine squared of Q1 plus sine squared of Q1, which this turns out to be 1. That equals 1. So I'm going to do this. So in this case, my P along P1, which is P along theta, is going to be M11 Q dot 1 plus M12 Q dot 2. Yes. This one was 0, M12. So that one is M11, which was MQ2 squared times Q dot 1, which, let me rewrite it nicer. This is M, not L, M R squared theta dot, and P2, which is momentum along R, is out. Oh, no, don't do that. No, I don't want this. Okay, sorry about that. PR is M21 Q dot 1 plus M22 Q dot 2. The first one is 0. The second one was M times Q dot 2, which is M R dot. So notice that the generalized momentum about in the direction of theta is actually the angular momentum. Angular momentum about the origin point O, where my generalized coordinates are defined, and the one along R is actually linear momentum. Momentum along. This is along direction. Let's call it ER. So along the direction of the vector R. So you can see, again, as before, these generalized ideas, well, not generalized ideas, momenta about these generalized directions or along generalized directions actually often have quite physical meaning. And they are the momenta about or along those directions. So that is all I have for now. So we have seen a lot of things in the generalized coordinates and in configuration space. What we will be using later is using these ideas to simplify the analysis of our system. So until then, happy studying.